can be found using this theorem. Yeah, so this is on this my official part of my topic is finished. And so we can discuss various questions.
Maybe any questions about the official part of the talk?
Lots, but hard to formulate correctly.
Please ask. Don't hesitate.
Yeah, maybe I can say a couple of words why, how it's related actually to the usual V algebras. Actually, this is the way how I came to the Lie conformal algebras. Actually, it's very easy. So let me explain. So let me return to the Virasoro algebra. Just the usual Virasoro algebra, which everybody knows. So all of you know this commutation relation. And this is the central one, right? Of course, there is another famous example. Let's write this down. So this is Virasoro algebra, and this is affine algebra associated to a finite dimensional algebra. Of course, the traditional way to understand it is that this V algebra G hat is Laurent polynomials over G plus the central extension, and you denote by an the element AT to Z. And this is the brackets. Okay, so we have this. But now the basic idea, one of the basic ideas of conformal field theory is that there are many much more complicated algebras like n equals 1, 2, 3, 4. Superconformal algebras, which you have to write pages and pages of comedy. But there is a simple way to simplify it and make it much more understandable. Then you have to introduce generating functions. And here A of Z. Which actually are future fields of the conformal field theory. And then why you do it? Because then these commutation relations can be written down in a much more concise form. Namely, this commutation relation is equivalent to this one. No. I think I need to here. where this delta function, which is usual delta function, but one can write it also explicitly in terms of the bilateral C, delta CW, is the inverse. Okay, it's a very easy exercise to check that this is exactly this. If you compare coefficient of z to the m, w to the n, then you will find it. And similarly, for this example, you have something like this: a of z equals a. So these commutational relations in terms of coefficient can be written in terms of this generating series. But after that applies the Fourier transform, which basically means, as everybody knows, replace delta, the i's derivative of delta, by lambda to the I. So what do you get from this? From this you get L lambda L. And you know this by the lambda break. So what the right hand side will be 2L times lambda plus L prime plus lambda cube over 12 And what this gives? This gives A lambda B is equal to AB plus lambda AB But this is exactly the lambda brackets which I wrote in the transparency. So this I call the Virasoro-Lie conformal algebra. And this I call the current, maybe affine Lie conformal. So both of them are related to certain infinite dimensional algebras. And it is not difficult to prove using constructions that actually I explained here. There is actually a correspondence, more or less bijective correspondence, between Lie conformal algebras and infinite dimensional algebras, which are spanned by this kind of generating series. So it also at the same time gives classification of a certain class of infinite dimensional algebras, which I was mainly interested in.
Where did the lambda bracket come from? Why did you think of it? How did you think of using it? And how did it first arise?
Yes, it's hard to say. It's basically in the classification of these algebras, which I call formal distribution algebras. You know, to classify them, I realized that they can be encoded in terms of these Lie conformal algebras. So to classify them, one needs to classify the Lie conformal algebras. And only then I noticed that there is relation to the differential algebra. Maybe it also would be interesting to see directly the connection between infinite dimensional algebras and differential algebras.
Yeah.
But as I said, if you consider non-local lambda brackets, then any connection, I think, with the algebra disappears because you cannot put lambda equals 0. You have a Laurent series in lambda inverse. And possibly, and I don't think there is connection to differential.
this way of writing Virasoro, which of course is the usual way, the trouble is the bracket then is not differential rational.
Yeah.
So it doesn't fit either. I think of Ritz first substitution algebra, I think of that as sort of Virasoro algebra.
Yeah, exactly.
But it looks so different from this.
Yeah, but the only way I know how to write it is to construct from infinite dimensional algebra the Lie conformal algebra, and then from Lie conformal algebra
so you have to
by using this function. That's amazing. So it's exactly the reason.
But the Lie bracket in the Ritz substitution algebra, right? It's so easy. The Lie bracket of FG, elements of the differential field, just F delta G minus, it's the Wronskian.
Yes, so let me explain.
It's so easy.
Let me explain you how it is related to this one. Because what it is, so let me just erase the central charge. Complicates a little bit the matter, but this is equal to G plus 2 lambda applied to L. Okay. And then, as I said, you write lambda equals minus delta 2 and G equals delta 1 plus delta 2. So from here you say you find that U lambda V is equal to delta 1 minus delta 2 applied to UV. So that is U prime V minus UV.
Yeah, okay.
I of course explained it on transparencies in a general situation, but in this case.
But this is, so that, yeah, this was just one special case of something very general. I think it was
Virasoro. Why Fourier transform? Any transform you can.
I must say that first I just saw that it is quite ugly to write everywhere delta function. That it's better to replace nth derivative of delta function by lambda to the n. And indeed it looks to be much better. But then, in order to prove properties, first you prove them in this complicated notation, which is rather long. But then I realized that if you introduce Fourier transforms, then everything becomes much simpler. So it was kind of technical device to simplify computation. Anyway, you can read about all this. Okay, about these foundations of the theory in my book Vertex Algebras for Beginners. I think before talking about vertex algebras, I introduced this formalism, which really explains. Now, can I ask a question? Yes, the first question is that you remember I stated the theorem that any finitely generated as a COD model Lie conformal algebra is either Virasoro or current, one of the two. Is there such a theorem for differential algebras? Hasn't been known such a.
Could you write it down?
I can state it in the language of differential algebra.
Okay.
Any simple finitely generated differential algebra. This is the morphic.
Finite dimensional?
Yeah, finite dimension. Fine, yeah, fine.
Yeah, sure.
So E is the substitution algebra. Or to simple finite dimension.
Substitution algebra. To A, to the,
Either or.
what do you mean by the substitution algebra?
To either,
Either.
either. Substitute.
Yeah. To A, substitution algebra?
But there is
But
only
then
one.
Oh, you mean of rank 1?
Right.
Ah,
Yeah, right?
yeah, yeah.
That's a substitution algebra.
Oh, that was Brits.
Pardon?
In this one, U prime V minus UV prime.
He just defines substitution group to be actually a group law on,
Oh, yes.
I don't know what you call it.
Or finite
Group laws.
dimensional algebra, say UI
It's just
J
group chunk.
equals sum CIJ K.
Yeah.
What VIV chunk.
So this is a substitution algebra is a Lie algebra structure on the additive group of the field.
Right.
You know, the interesting thing about that is I can't get the usual central extension. It doesn't exist in this theory, and the reason is that the substitution algebra is a Lie algebra structure, differentially rationally expressed, differentially polynomial bracket. It's a Lie algebra structure on the additive group of a differential field.
Right.
And that's what we call strongly connected, which would mean there cannot be any two co-cycle from the group across the Lie algebra across the Lie algebra into a Lie algebra of lower type. The kernel, the central extension is one-dimensional over constants.
Right.
The additive group has what we call differential dimension 1, and you can't go. You can't have a two co-cycle.
No, of course, in deconformal algebra,
So what you can
you
have
take
central
every
extension.
module of polynomials in D, in particular the one which have torsion. You can take, for example,
Yeah.
one-dimensional module plus a constant.
Yeah, it exists, but you can't get it from a two co-cycle.
No, but
Usually
in my
it has
transparencies,
a-
I wrote what should be the bracket. You just term integral,
Maybe you can.
the third derivative. Yeah, for example, here
Oh my God.
you in this form you
You
just
define
add.
the bracket, but it isn't given by a two co-cycle. If it is, we're in trouble.
Yeah, this is the terms that you have.
See, it doesn't, it's that device. The device where you take V mod dV and call that
Right,
the elements, functionals, that call them integrals.
right.
That would be very nice. Would that be in our category though?
It depends how you define the
Maybe.
category.
See, that integral isn't an integral. I mean,
Integral by definition just
That's
canonical
good.
map from
I don't
V
want
to
an
V
integral.
mod dV.
yeah, maybe you could make it work. Yeah. Yeah.
Okay, but this without central extensions.
But this
is there
was
such a
not
thing or
yeah.
not?
Or simple finite dimensional.
Yeah, just
Finite dimensional Lie algebra. All the concepts. Yeah, sure.
no by differential. I wrote the bracket. It's just V UI Vj equals sum Cij K UI Vj.
Okay. And And the structure constants are just in,
of simple finite dimensional.
oh, okay.
So no derivatives are
Finite
involved.
dimensional. Well, if it's the Lie algebra of a differential algebraic group, the answer is yes. It would be simple finite dimensional Lie algebra over constants, actually.
Yeah.
We want a Chevrolet. I should call it, I don't know, Carton.
And a finite dimensional in sense of just finite. In what sense is it?
You finite type.
Yeah, finite.
No, but if you don't assume.
Oh, wait, what's a simple finite dimension?
Yes, what does it
Yeah,
mean?
what do you mean by simple finite dimensional differential Lie algebra? Do you mean finite dimensional as a vector space? The underlying
No,
vector space?
yes, that's why I wrote not finite dimensional.
No,
Finite.
you didn't even write that. You wrote some, yeah.
Finite. So you have finitely many UIs.
Ah. Finite many UIs, where the UIs,
Differential values, it's probably my right. Actually,
how do I do it? I don't know what that would be.
oh, so there is such a theorem, you know.
I'm not sure what you mean by simple finite differential Lie algebra.
But
Do you mean the differential, for me, differential Lie algebra has to have underlying set, the set of solutions of a system of algebraic differential equations. Actually, linear.
Okay, maybe I should.
Differential
I
polynomial.
should just show.
In other words, it has to be the additive group has to be, this is the best way to say it. I'm not saying
Yeah,
it
maybe
right.
I didn't.
The additive group has to be a differential algebraic subgroup of GA to the n. In other words, a set of solutions of linear homogeneous
Let me
partial
show my
differential
definition.
equations.
Maybe it's completely wrong. Yeah, this is the definition.
Oh, okay.
So the bracket is of this form.
Yeah, by differential polynomials.
Yeah, the QID.
Yeah.
This is differential.
Okay, I understand, yeah.
So is it true that any
I don't know the
simple one
answer.
is one of the two?
What about the underlying vector space? Let's see, is that, there are two possibilities. Either the underlying vector space is a finite dimensional vector space over a differential field,
the
but the
universe,
lead
right.
bracket would have to be
Exactly.
C-linear.
Right.
Yeah, that,
Right.
yeah, those were the ones I started looking
this
at
is the definition.
when I was looking at this material
Right.
of Ritz.
But Felix, what about the Lie algebras that correspond to just differential algebraic groups that are not constants? How did they appear here?
They wouldn't come under that definition.
No?
No, that definition has to be, the underlying vector space has to be a finite dimensional vector space over a differential field, and a Lie algebra over the field of constants of that field.
But,
So essentially, Lie algebra of operators. And then the bracket is given by differential polynomials. When, for example, you classify the, say, simple Lie algebras, differential algebraic Lie algebras, then they're conjugate to Lie algebras that are Lie algebras over fields of constants of algebras of that algebra.
You said that it's similar to learning.
Yeah. Well, for the algebras, it probably goes back to the classification of the Lie algebras. Certainly Cartan would go back to Cartan.
No, but he didn't probably consider differential algebra.
Oh, no, he didn't. That's the trouble.
But so when I explicitly talk about it.
Yeah, the thing is that I used my definition of the algebra, and I got one of Cartan's lists.
Associative.
The list of, I think it's intransitive Lie algebra structures on two-dimensional, on a two-manifold, on the plane. The intransitive ones get the same list, only something left out. So it must be the same definition.
But for, what,
He's looking at pseudo, at his groups.
But what was the simple one?
These are the simple ones. I don't know. It's
I told you that I don't understand the connection with the definition with some other definition which is used also in literature.
Of differential algebra.
Yes, for instance, in Cartan you have pseudogroup of Lie algebra, which are Lie algebra of a vector field of a variety,
right.
defined by some differential equation with the property that the bracket of two solutions is again a solution. So it's the object you get when you write equation which fix some differential structure.
Right.
For instance, you take a differential form or something like that and write the vector fix which fix that form. So you write a differential Lie algebra in that sense. But I don't understand.
With differential algebraic Lie algebra.
Yes, but
Other than differential Lie algebra.
Right. That's how I get that. Remember, I
the
get that same
differential Lie
list.
algebra corresponding to differential algebra group of
Right.
fields are not exactly the definition,
No.
but close from that. Since you start with the family of Lie algebra over C, and you look at differential equation, again, which are compatible.
Right.
It's over C. Here in Cartan, it's not over C, it's a differential equation of first order. And now,
Right.
I don't understand what is the relation with your definition, because you have other differential Lie algebra.
This
What
was
are the relations?
when I was
Yes.
reading papers for Phyllis, this was
Yeah.
my understanding.
That's the
different algebra with a derivation, right?
No. These are actually differential Lie algebras in the same definition I use.
So it's equivalent?
Yeah.
It's equivalent.
It's equivalent. And that's how I get the same list as Cartan.
Oh, yes.
Of the intransitive ones, the ones that fix.
Yes.
Yeah. So it's the same exact list. I was very surprised.
But in this definition, where are the algebraic relations?
Differential rational.
Why?
Yeah, what are the differential equations?
In other words,
Well, these.
what are the defining differential equations? Put it that way.
That's a very hard question.
Yeah.
So if you start with structure equations and you want to know what are the
Right.
what PDs does it come from, that's sort of a very wild question, right? You
Yeah.
have to sort of compute all the differential invariants at all levels of your pseudogroup,
That's right.
and then
They're not
find all the
presented in
constraints.
that form.
Yeah, so-
But you can prove that there exists a system of equations satisfying it.
Right.
Yeah.
Okay.
Well, because I'm presented
So-
with it in the right.
Right, I mean, and so everything Cartan does in terms of these pseudogroups, he says, suppose we have so he always works, say, on a manifold or on a variety of some sort, right? It says we have some subgroup of the automorphisms of this object,
Right.
and suppose that we're dealing with the object whose trajectories are given by solutions of differential equations. Then we'll prove these statements. So that's already assumed that you're having a system of PDEs behind everything.
Right.
Otherwise, you can't do any work because everything
Well, that's
relies on
what I
bicellular.
said too.
Right.
Yeah.
But he doesn't, for instance, require that the structure coefficients, the Q's, be polynomials, right? They can be arbitrary involutive, arbitrary functions, right? He requires them to be, of course, power series, but that's because he's working over You need special list.
And,
Yes, yeah, of course, it's essential that they are finance, but there are not many examples in videos. There are some.
these are three polynomials.
Right. There's certainly geometric examples where you have pseudogroups where your structure coefficients are actually, functions, but
Right.
whether
But not here.
They're not here.
No.
Of course not.
Yeah, at least polynomials in vectors, coefficients.
Right. Right. So getting back to your question, suppose we assume.
So we have differential algebra in this sense. We utilize with J in some differential, as you call, universe.
What about the rank 2 list?
It's just there are no simple ones at all.
There are no, oh no, that's right, they're all, yeah, in fact.
It's only the rank 3.
Yeah. And the ones of finite type are nilpotent solvable? Yeah.
So the linear are just any simple algebra, that's all. And beyond linear, there is
That's a
only
good
one.
question. Right, they're not simple. That's a good question.
And you wrote that you said that you wrote a paper where you classify.
I classified differential algebraic groups that are semi-simple. But the way I classified them is the way I always had to classify anything, and that is classify the Lie algebras and pull it up via a map we have called the logarithmic derivative. So
Okay, but for Lie algebras,
the Lie algebras,
you use just the usual classification.
but I followed Chevrolet, which is very beautiful. The way Chevrolet does it. Very intensely algebraic, geometric.
But he didn't consider differential fields.
He has papers on the Lie algebras, the semi-simple Lie
Or with
algebras.
differential fields.
No. Oh no, I had to go past what he did. But it falls out miraculously from his work. I used the notion of a Chevrolet basis. And the definition of a Chevrolet basis makes it the differential algebraic subalgebras fall right out of the definition of a Chevrolet basis.
So you prove that in a simple differential algebra there is always a Chevrolet.
Yes.
So you choose
You just-
subalgebra.
And the reason you get conjugacy is you just change the Chevrolet basis. You have to prove that there always will exist a regular element in the differential algebraic lease of algebra. But that's trivial. It turns out very easy. So that's the paper I dedicated to Marty's. Yeah.
I understand.
Yeah. Well, I could. So it's in. Where is it? Where did I find
Journal
it?
of
I think
Algebra.
87.
Journal of Algebra.
87.
Yeah.
Question mark.
But that's a good question.
About isomorphism of these objects. So, in the case where Bertrand's studying these pseudogroups, the notion of isomorphism is that above, two objects are isomorphic. If there's someone sitting above them,
Prolongation.
right? You can you can sort of find what's the right? It's not really a prolongation necessarily, but it's, a loose pseudogroup above them for which each of them is a projection. So
that sounds a definition of isogynous.
right. So this was back in 1912 or 1913. Right?
I didn't know that.
So
It's for groups.
for infinite dimensional least groups, yeah. So how tricky? I mean, you're talking something like that. It looks like you can just say, "Oh, isomorphism means what I think it does." Is that true, or is there some subtlety to it? Because because you have to, and
Yes.
you have to move, you have to move everything, right? So you need to move your notion of your differential operators and the underlying space, of course, and all the structure coefficients. But is that all that you need to do?
Yeah. So basically conformal algebra is just kind of traditional algebraic strategy.
Yeah.
Except that
Because this is still an open and very active question. Is
Oh, is it?
yes. If you want to know, the person to talk to is Peter over at Minnesota.
Oh, yes.
Yeah, so he's, and also, who else would be, probably someone like Boris Kuklukov also would be
Yes.
the expert in that. So,
Yeah.
but it comes up all over the place that
Right.
you want to study one or two. It's actually very much analogous to the notion of like a Beckman transformation for a system of PDEs.
Right.
We have to find something to move it through.
Right.
Otherwise, there's no way to compare them. So.
Yeah, we have that same definition of Versace, but in a paper that Michael Singer and I wrote, we came across an example of Cartan's. And Cartan claimed that these two groups, yes, for me they'd be subgroups of the additive group. These groups were not isomorphic in this sense, but we had no idea what that meant.
Right.
So we decided to show that it's not isomorphic in our sense, and they're not. So we're still left with the question, what is the difference between Cartan's definition of equivalence and our differential rational differential polynomial isomorphisms?
If you want to investigate, there's some very well-written papers by Peter Over and Ua Pohenpelto and
The second name.
Pohenpelto, P-O-H-A-N, not P-O-J-A-N.
Did he write with Peter?
Yeah, just look up Over and Pohenpelto. And Mark Fels has a few things in there too. Mark Fels, F-E-L-S.
And what is it about?
Oh, about the notion of basically just finding the structure, finding invariance of least groups is basically their game. So they say, here's a least group I want to study, and they have a way to compute all the invariants in all their sysgs, and then they're using that to go back and analyze these notions of isomorphism that Cartan had, and say, well, that confirming that the different sysgs will match up in an appropriate way if you have this sort of that shape. So.
Yeah. I don't understand because he was supposedly very clear, Cartan. He wrote several articles defining what he means, but I don't know.
I've never heard anyone describe Cartan as clear, personally.
Very not easy to read? Oh,
It's not easy.
no, not easy. I was going to say you'd be the only person ever born. But it's fun reading it. So I'll think about that. But I suspect the answer is no.
I think it's not wrong.
Yeah,
Why?
I thought it was yes before, but
Why?
I don't know though. Take that back. Good question.
But what do you call type? Because
Type. There's the expert right over there.
Well, something else. So that's.
No,
Oh, well, I actually know what you mean by type. Classically, which is a poor imitation in a sense. If you have a general solution, whatever that means, then the general solution, let's say, let's type and typical dimension. So as the type is tau, which is what Colchin called it, then that's the number of independent variables on which the general solution depends, and the typical dimension is the number of what? The arbitrary functions of tau independent variables on which the general solution depends.
It's the coefficient and degree of the Hilbert polynomial of the Hilbert scheme.
That's exactly so that Colchin has a Hilbert polynomial equals a dimension polynomial that has a certain degree, that's the type, and leading coefficient, that's the typical dimension. And in our, if something's strongly connected, that means you can't have homomorphism to something of lower type. So you can't depend on fewer independent variables. You depend on tau independent variables, you can't have a homomorphism in our category onto a variety that depends on fewer than tau.
I have no idea what your category is.
What?
I don't know what category it is.
What the category is? Yeah. The solutions of algebraic differential equations, those are the geometric objects. And the homomorphisms are expressed essentially differential polynomials in the coordinates of the elements of the pre-image of the source.
It's terminology in differential groups that kind of hierarchy of differential groups.
Ritz definition?
Right. With the
Yes, a finite
lowest
type.
is-
You couldn't go from substitution type to finite type.
Mhm.
If the substitution type was strongly connected. This is a generalization of connectivity in algebraic geometry.
Mhm. These kind of
It's-
reducible varieties in
Yeah.
the category of algebra.
Yeah.
Differential.
Mhm.
But so you're saying that my definition here on the transparency is the same as your definition.
Yeah.
So,
Yes, but I better write that down.
But here's
I
the
don't
type.
understand.
I'll
I
send
don't
it.
understand why.
Yes, the type doesn't appear here. I didn't, type
No.
doesn't appear.
Uh,
When you talk about the algebra, it's only when you talk about groups that the type appears.
no.
Also when you
I
talk
mean,
about,
but the trouble is, I can't prove that if you have a Lie algebra that, yeah, right, a Lie algebra of a differential algebraic group, that they have the same type. Oh, yes, they do.
Yeah, no, they do.
What can I prove?
That's what you have.
Oh, if one is strongly connected, if the group is strongly connected, why should the Lie algebra be strongly connected? I don't know that.
No, that we don't know.
Yeah. Yeah.
what
But
does it mean
that,
strongly
but that,
connected?
that's not what his question
Strongly
is.
connected.
Means-
So that's not what his question is. His question is, where does the differential type, or rather, different dimension comes in, polynomial comes in the
Because
differential algebra here?
the underlying set
Yeah,
is
right,
a differential variety.
right.
Because it
But I
just,
don't- To me, I don't see why this
You
was
can't
a-
see it here.
Yeah, you don't see it here.
No.
Yeah, you won't see it until you actually start looking at what orbits look like, right?
There is a problem that for group, if you have a family of group with differential equation compatible with that structure, that means it's a differential algebra group in general, you can reduce by a theorem of Pillai to the special case. You consider that for Lie algebra, theorem is not true.
Oh, what do you mean? Sorry.
You have two possible definitions for differential algebraic group. One, you have a family, you have a group over a variety, or a family of group over a variety, plus,
Oh, I see.
plus differential equation, which are compatible with the group structure.
Right.
But the group structure is not differential. And a more general definition would have differential group law.
Right.
That's
So
right.
now,
That's what I have.
yes, but Pillai proved that you can reduce the general case to the special one.
Who did?
Pillai,
Allah Anand?
yes.
He
yeah,
did.
he has a big point.
But for Lie algebra, it's not true. And
Not
that is
true.
the difference. For the Lie algebra, for instance, the bracket, the Lie bracket, you cannot reduce the equation of
Oh, that's coming.
It's first order equation, you cannot reduce to order zero. So the theorem of Pillai is true for group, but not for
No, I don't understand.
It's the umbrella,
You
yours?
understand?
Is that an umbrella?
Yeah.
Yeah.
If I understand the theorem
Wait.
of Pillai, theorem of Pillai was an old problem of Colchin. In fact, it was an old problem of Colchin, but I don't remember how it was posed in terms of Colchin. But it means that you can essentially reduce the equation of the group to zero order equation for a differential algebraic group.
For anyone, not necessarily.
To zero?
Yes.
Zero order.
Order.
Oh.
Oh, yeah, but that's Pilay's.
Oh,
That's
Pillay.
Pillay. That's
Pillay
Pillay, yeah.
proved, only we don't understand the proof.
Yes.
And he only proved it for ordinary.
I found that was not clear. Oh, yes.
So that the primes don't appear, just the functions.
It was,
So,
Oh, I get it, yeah. You
so
can
take,
embed.
take a general definition that you have
Yeah,
low group given by differential equation plus some other differential equation compatible with that low group.
Even the law.
And so Pillai proved that you can omit, you can reduce to the case where your equation for the group, algebraic equation.
Algebraic equation.
But for the Lie algebra, it's not true, because the obvious counterexample is the Lie algebra of vector fields, which is given by differential equation of order 1. So therefore, Lie algebra of vector fields, it's your definition. It's yours with some Q of order 1.
Right.
But
Okay.
more special definition would be to have algebraic family of Lie algebra plus differential equation compatible with it, which is the case of the Lie algebra you get when you take Lie algebra of differential algebraic groups.
You mean,
And so, I mean, your definition is more general. in my opinion.
yes, that's because not every Lie algebra is the Lie algebra of differential algebraic group.
Yes.
Because what
This
Pillai
is a
proved.
substitutional Lie algebra. Is the Lie algebra differential?
No.
It's a Lie algebra
that's
of
right.
a formal differential group, but not of.
Not
That's right, of the formal group.
No, you have no group with the
Well, you can make a group,
Lie algebra.
it's a pro
Lie
differential.
algebra of
Yes.
Cartan, if you want to integrate, you find the group of automorphism, local automorphism of your variety,
Right.
but
Yeah.
you don't find the group.
Yeah. There is no sort of.
So
Yes.
what Pillai
Yes.
proved is that he proved over ordinary differential fields, every differential algebraic group is embeddable by a differential rational map in an algebraic group. So then that rationalizes everything. And then
So
it's Lie
embeddable,
algebra.
So it's embeddable.
Yeah.
What you have
Yeah, sorry.
is just differential equation.
Right.
We have an ordinary family of groups plus differential
Right.
equations.
And then, of course, the Lie algebra, we take the differential of that map, and the Lie algebra is mapped into the Lie algebra of that algebraic group. So it rationalizes everything. But this would not, certainly could not be done that way.
And
But that's not
it's
the Lie
So
algebra.
your definition is, so your
Yeah.
definition is more general.
More general. Well, but not,
Well, I mean-
yeah, but I worked on differential Lie algebras too.
Oh,
You
yes.
see, the trouble is I
So
abandoned it after I wrote that. I want to
So-
get back to it because there are more
So-
interest,
so
a lot
you-
more interesting ones.
Phyllis, are you then saying that in this definition of differential Lie algebra is that the bracket law, so to speak, right, is given by differential polynomial, right? Okay. Now, but in a differential algebraic Lie algebra, it would be a Lie algebra, ordinary Lie
No,
algebra.
that's a differential Lie
Wait,
algebra.
Plus differential
I want
equation.
to see if there is a difference, okay?
Plus
There-
differential
there are-
equation.
There are two things, right? I mean, to me, right now. One is this definition, which is a Lie algebra whose bracket law is given by differential polynomials.
Yes.
And that makes it a differential Lie algebra.
Wait, okay, you're saying that it makes it a
Yes.
differential?
Makes it a
No,
differential
no,
Lie
no,
algebra.
no. It is by definition called differential Lie algebra.
Yes.
Yeah.
Let's take it that way, all right? The word
okay.
differential Lie algebra means a Lie algebra whose bracket law or algebra, structural laws are given by differential polynomials.
That's right.
Okay. Now, there is a Lie algebra whose elements, all right, in a differential setting satisfy differential equations. In other words, there is a derivation on the Lie algebra, on the elements of the Lie algebra, and the elements themselves satisfy differential algebraic equations. Now,
There's a derivation.
that would be what I would call a differential algebraic Lie algebra. Just
No.
like you say differential
not
algebraic.
any that I know
Okay,
of.
fine. I'm asking you,
Yeah, what are you asking?
all right, is there a difference between the two?
There doesn't need, in a differential algebraic Lie algebra, there need not be a derivation defined on the Lie algebra. That's an added thing.
Okay.
So all it has to be is,
William was not saying that the derivations on the Lie algebra.
it's not they're not derivations
But he's
on
not
the Lie
saying
algebra.
that.
They are linear differential equations.
Yeah, exactly.
Yeah.
That's
They're linear
so the first
differential
definition is everything.
But this differential equation
Differential
have to be
algebraic.
compatible with the list.
Absolutely, yeah,
The two solutions, the bracket of two solutions is a solution.
that's right. That's
So it's
right.
another definition. You would have something more general if you take first your definition and you take the sub-bundle defined by differential
Right.
equation.
See, I
With
mean,
that compatibility.
see,
with that
the thing is that
have something
let's look at differential algebra. Let's look at differential algebraic geometry.
sub-differential algebra, pure differential algebra. So,
In-
but what one has in differential algebraic groups is there's equation, but with group law algebraic, with the algebra group algebraic. The algebra, which is algebraic equation, plus differential equation.
Now,
And so in your situation, you can have both. For
No,
instance,
I'm still-
for instance, in lithium group,
can we?
Cartan theory, you take
Just a minute.
the algebra of vector field, which fix one differential structure. You have first the bracket, which is given by
Differential polynomial.
differential equation, and second, phase equation. So you have both.
What is the second? Excuse me?
The second
should be
equation,
satisfied
which
by
is,
elements.
yes, take, I don't know, take the vector fields of a variety which are symplectic or preserve the volume. You have a differential algebra in this sense, which is the differential algebra of all the vector fields of the variety, plus a differential algebraic condition.
Fix.
Which makes it a subalgebra.
Yes.
Yeah, because
Zero
there are two problems. For example,
Divergence.
in Lie groups. One problem is to classify, for example, simple Lie algebras. Another question is to classify the representations.
Yes.
This completely answers the
Yes.
question, what are all simples about? But I'm talking about the first question. Let's just classify simple Lie conformal algebras, abstract.
Yes.
After that one can actually classify also all finite dimensional representations.
Yes.
Right.
So,
So this brings up something else, and that is if you take, say, the vector space of, take delta, our distinguished set of derivation operators, delta 1 through delta n, and take what I call F delta, which is all linear combinations of delta 1 through delta n with coefficients in F. So those are derivations, they're all derivations, all linear combinations
You
of
like
delta
to
1
say comment?
So that's where this comes in. Then when you compose two of those operators, you get a law like this, where you have,
No, but here I consider just a case of one derivation.
yeah.
Delta 1, delta 2,
And
and
you
delta
can do it
1
with
acts
one,
as the
too.
first factor.
Yeah, you can do it with one or several. And then, so it's a vector space, this is a vector space over a differential field F and a Lie algebra over the constants of F, the field of constants of F. Because the Lie algebra has, the bracket has coefficients that are differential polynomials. And so therefore, the bracket is just C linear, C bilinear,
Yeah, of course.
not F bilinear.
Yeah.
And then, once you have that structure, you can either look at substructures that are exactly like it. In other words, you take a subspace of the vector space that's closed under brackets that always has a commuting basis. If you're working over a field. Oh, so that would be the substructures, exactly like you'd have a set of commuting derivations and linear combinations of those with coefficients in F, and it would be a Lie algebra over C. Or you could say to yourself, well, the ambient structure is also a differential algebraic Lie algebra. And that would mean, if I'm looking at its substructures, then I would look at the objects that Bernard is describing. You wouldn't be looking at vector spaces over F, but you'd be looking at Lie subalgebras of the C Lie algebra structure that satisfy partial differential equations.
Mhm.
in the coordinates, which would be the coefficients from F. You start out with D equals summation Fi delta I, and then you look at a set of those that satisfies a system of partial differential equations and the coefficients. That would be the differential algebraic lease of algebras. But I don't know. You're looking at something different entirely?
Pardon?
Are you looking at something different entirely?
No.
No? Yeah.
What I understand before
Yeah.
that, but
Yeah, but this,
I think there's some confusion in the literature.
it depends on what structure do you put on this object? That's
Then of course there has to be a bracket.
That's the original.
You need to.
Go ahead.
Okay. My misunderstanding, if you like to call it, right? Is, you see, you start with like differential algebraic geometry. You know, let's say you have an affine space. So in this case, it's A to the n, right? Where
Affine space.
Affine space.
F to the
Let's say
n.
if A is a differential field, all right?
Right.
Okay, then we have affine space. Then you can talk about subsets of it, differential varieties, algebraic varieties, which satisfy differential equations. Now, if that happens to be a Lie algebra structure, as a Lie algebra structure, then I would think that that's called differential algebra.
No, it has to Lie algebra.
That's the same way you call a differential algebraic group.
No,
Yes.
no.
A different, well, I mean, there are two ways.
No, you're misstating what I call a differential algebraic group.
I know, but your definition of the algebraic group is that the structural maps are differential rational
That's
maps.
right.
Okay.
That's
Yes.
Colton's too.
Okay.
They have to be differential
And
rational.
then you prove that such a group satisfies differential algebraic equations. Is that right? Does it
No.
satisfy? No.
You start out with what you're talking about.
See, when we are
I'll just
talking
add-
about
no, I'll just add
linear,
one.
let's look at just linear differential algebraic groups.
What do you mean by linear?
Sitting in GLN,
Oh, okay.
right? So this is
German
GLN
GLN.
of some differential fields.
Yeah.
Okay. Now the group law structure, of course, is differential algebraic. It's algebraic even.
Sure. It's big.
Right.
Yes, but that's
Yeah.
But we look at it as an affine space, n squared space, right? And then we look at whether it satisfies differential equations. Now why? So in general, why should be the two things the same? Mean the same thing. You know, the fact that a differential variety.
That's not true.
What is not true? I haven't finished.
Oh, but I know what you're going to say.
Okay, what am I going to say?
Go ahead.
Well, tell me what you think I'm going to say then.
Are you going to say that just because it satisfies, it's a differential variety, so to speak,
Yeah?
that it has an additive and it has a Lie algebra structure over constants, that Lie algebra structure is given by differential?
No, I didn't say that.
Oh, okay.
I didn't say that.
No.
That's why I said
Sorry.
to me there are two concepts, and I want to distinguish them. And you keep saying that sometimes they're the same thing. I don't know which one is which.
So what are your two concepts?
Okay, one concept is in the affine space here,
Okay.
right? Affine space, the whole affine space. You can put in a Lie algebra structure like here, which is given by differential polynomials.
That's right.
Okay, that's one thing. Now, what do you want to call that?
That's a differential algebraic Lie algebra.
Differential algebraic Lie algebra, not differential Lie algebra.
Well, that's just a shorthand for differential
Okay.
algebraic.
Oh, see, that's the confusion. So
No, because the underlying variety is the underlying set is u to the n or f to the n.
right. So therefore, it's all right, right?
That's a
So
group differential
that's
variety
right. That's
in the geometry.
right.
And the group laws are given by differential,
Okay.
quadratic usually probably,
Okay.
differential polynomials.
Okay.
I mean the Lie bracket in this case. And the scalar multiplication is given by differential polynomial, culture put that in.
Okay. But what if I add
That's it.
differential equation on it? Right now,
Yeah,
there's
okay.
right now there's no differential equation on it.
Yeah,
Basically,
because that's the ambient.
because the whole thing, right?
I see what
That's the
you're
whole
doing.
thing.
differential
Right,
equation.
okay. So now you have to take a subvariety of it.
Yes,
But that subvariety need not be a Lie algebra. Need not be closed
Right.
under the Lie bracket.
right.
So you want it to be closed under the Lie bracket as
That's
well.
right.
Okay, fine. That's fine.
And in fact, but if you start with that first structure, that has the possibility of having two different structures on it. The first structure is both a finite dimensional vector space over a differential field F,
Right.
Yes.
and a Lie algebra over constants, with
Okay.
its Lie brackets given by
Okay.